In today's lesson, we will talk about matter, its properties, and the changes it can undergo. Our learning targets include being able to distinguish between and identify physical and chemical changes, as well as physical and chemical properties. We will be able to explain how three states of matter, solid, liquid, and gas, differ from one another at the molecular level using the characteristics of each state. We'll also be looking at heating curves and cooling curves to determine how phase changes occur and whether they are endothermic or exothermic. And we will also be able to explain generally how chemical exothermic and chemical endothermic changes differ. Chemistry is the study of the composition, structure, and transformation of matter. And for today's lesson, we will be focusing on its transformation. Let's start by examining some physical changes. A physical change is when there is no change occurring in the substance chemically. After a physical change, you will still end up with the same substance at the molecular level intact. Physical changes, some tend to be reversible. So we'll talk about how to distinguish between ones that are reversible and ones that are not. So let's look at this example of blending fruits into a smoothie. So if you were to just simply mix the fruits in the blender without pressing the button to blend them, you would be able to retrieve the fruits from the blender intact, right? But as soon as you hit blend, you're now causing an irreversible change. You can no longer get that apple back in its original form. The vitamins and minerals, all the nutrients that are in those fruits, though, are preserved and stay blended in that mixture. So because the integrity of those molecules is there, we say that blending or mixing is a physical change. Another example of physical change involves bending and sculpting. For example, in this animation, we have a hammer pounding on a nail. So nails are usually made out of metal, and metals can easily be bent. They can be used for sculpting purposes as well. So metals are used in creating jewelry because metals have the property of being malleable, which means to be able to bend and shape. And they also have the property of being ductile. So ductile is when you can take metal and make it into thin wire. So if you explore electrical wiring and you understand what it's made of, it's usually made out of metal because not only are metals ductile, but they're also excellent conductors of heat and electricity. So shredding and tearing, if you rip up paper, it's still paper, right? So you're just in smaller pieces. That's an example of an irreversible change though, because as soon as you rip it up, you can tape it back together, but it's not going to look the same. Now let's take a look at some examples of reversible physical changes. So this is an example, the picture of the snowman with the bowl of soup in front of him. This is an example of a few different types of phase changes occurring. So in order to make the soup, you've got to boil your ingredients together, adding the water. And what's happening here is the bowl of soup is steaming, the water is evaporating. So that's a phase change, the boiling and the evaporating. And the steam from the soup is causing the icy snowman to melt. So that's another example of a phase change. So H2O, whether it's in water vapor or steam form, in gaseous form, or whether it's in liquid form, or whether it's solid ice, it's still H2O. So because its molecular structure remains intact as H2O, we call that a physical change. A phase change, a change of state of matter is simply a physical change. Sublimation is another example of a physical change. This is a sample of dry ice, carbon dioxide in its solid form, going straight from solid to gas. And when that happens, that process is called sublimation. So when you take dry ice out of its frozen environment and put it put it on a surface that's at room temperature or in an environment that's at room temperature, it will immediately sublime. The opposite of that phase change is deposition. So deposition is going from gas to solid. So here's an example of hail, a picture of hail. Another example of deposition is snow. So those weather changes that we generally pray for every winter, those of us that are students or teachers, those are examples of phase changes or state changes in states of matter. So those are all examples of reversible physical changes. All right, we're going to now examine 3 of the states of matter. Now, there are more than 3 states of matter, but for our purposes in this course, General Chemistry, we're going to focus primarily on the states of matter that we come into contact with on a regular basis in our natural world. So the first state we will look at is the solid. So if you take a look at the picture, you'll notice that the atoms of the solid are slightly vibrating and that they have limited free space between them. They're not moving very freely. So because there is limited free space between the atoms, they are not easily compressed. There's no space left for you to push them any closer together. They have a rigid structure as a result of the small amount of space between them, between the atoms that make them up, and there's no easy flow of a solid because of the fact that they're rigid. They have a fixed shape and a fixed volume. Now, if we take a look at liquids, the liquid phase, liquid molecules or atoms are also not easily compressed because their molecules also are rather close together. The particles have very limited free space. They do flow easily, so that's a difference from solids because the particles can move past one another, as you can see in this picture, or the atoms can move past one another. They assume the shape of the part of the container that they occupy. Liquids are also not easily compressed. If you, for example, had a glass of water in front of you and attempted to press down on it to compress it, you would not be successful. The water would spill out of the container probably, or at least spill onto your hand. So the reason for that is because, again, the molecules are too close together. So changing their pressure won't really have an effect because the molecules or the atoms that make up liquid and gaseous states aren't able to be pushed any closer together. They aren't able to be compressed. So with gases, you'll notice that there is ample space between the atoms. They're moving at a much faster pace, or their kinetic energy is definitely higher. Because of all of the free space between the atoms, gases are considered to be compressible. They flow easily, and they assume the shape of and volume of the container that they occupy. So gases expand to fill the entire container of the space that they're occupying. Also, notice how when you have the blue screen up, for the gas atoms, they are moving, but not as fast as they would if you heat up the environment. Notice they're moving much faster now because heat's been added. So when heat is added, then the kinetic energy of the atoms or the molecules that make up that gas also increases. Let's take a look at the heating and cooling curve. So we'll start by looking at the heating curve in black and white here in this picture. So you'll notice that as you go across the x-axis, heat energy is increasing. And then as you go up the y-axis, it shows an increase in temperature. So on this heating curve, you'll notice that as you increase the heat energy, the temperature is also going up. But then at some point, it stops increasing. The temperature stops increasing even though heat is still being added. So think about what that heat is being used for. Why isn't that heat being used to increase the temperature? What else is it being used for here? Then as we reach this point, the solid has changed to a liquid. Notice there's more freedom, a little bit more freedom of movement for the atoms here. And what's happening here is that the liquid is continuing to be warmed. The heat that's being added is increasing the temperature of the liquid, making the atoms move faster. And then again, once again, the heat energy is not increasing the temperature here. So what is that heat energy being used for? Think about that. And then once we reach this point, the heat energy, we've now changed the liquid to a gas, and now the gas is going to be heated, and the atoms of the gas are even farther apart because the kinetic energy of the atoms has increased, so they're able to move more rapidly and in that gaseous state. Now, for the cooling curve, this is an animation taken from the CK12 website, and it's showing the cooling curve animated. So we're starting at the gaseous state, and you can see as the temperature is decreasing, when you go backwards on the heating curve, we are condensing the liquid to liquid. And now we have a liquid and we're cooling it down. And when we get to this point right here, can you guess what will occur? So when we get to this point, the liquid atoms will begin to freeze. Okay, so we have a change of state occurring on these flat plateaus. And then once we reach this point, we now have reached the freezing point where the substance that was once liquid is now completely solid. And now we continue to lower the temperature and the solid is just getting cooler. So hopefully you understood that as we hit the plateaus, both on the heating and cooling curve, what the heat energy is being used for is to change the state of matter. So how is it doing that? How is it changing the state of matter? How is it causing the solid to become liquid by melting? How is the liquid becoming a gas by boiling or evaporating? How is that happening? So think about that as we go to the next slide. So the energy that's being added during a phase change is being used to overcome intermolecular forces of attraction. So forces of attraction that occur intermolecularly. So what does that mean? Inter means between molecules. That's what that prefix means. So think about it. As you add heat, what's happening is that the forces of attraction that are holding these atoms together in the solid state are being disrupted. They're being overcome. That's what that heat energy is being used for. Once they're completely disrupted and the solid has melted to liquid, now that heat energy is being used to heat up the liquid, causing the molecules or the atoms that make up the liquid, to move at a much faster rate. And then once we reach what's called the boiling point, the point of evaporation, that heat energy that's being added is then being used to continue to overcome the intermolecular forces of attraction between the atoms and cause them to spread out even further. So at this point, we have a phase change going on. We've got liquid beginning to boil or evaporate. And then once we reach the end point here of this line segment, now we have a pure gas. And then as you continue to go up the line here, you're continuing to heat up the gas, causing that increase in kinetic energy. So imagine now that these blue dots, imagine that they're molecules of water. Okay, think about what those intermolecular forces of attraction holding the water molecules together. Think about what they're called. You learned about this in biology class. So think about that. Pause the video. All right, we'll get to that answer in a moment. As we go up the curve, though, I want to remind you of different types of changes that can occur, different types of physical changes. We can have an endothermic physical change or an exothermic physical change. So let's look at the difference. If you have an endothermic physical change, that means it requires energy, it requires heat. So just think about the N in endo and just think that that stands for it needs heat or needs energy. So to go from solid to liquid to make a substance melt, that is an endothermic process, okay? And then similarly, to go from liquid to gas to make something boil or evaporate, heat is also required and that's why we call these phase changes endothermic processes, okay? The opposite is true when you're talking about the cooling curve, okay? So when you're going down the cooling curve and you are decreasing the temperature and causing the gas to become liquid or to condense, that's the name of the phase change, condensation or to condense, that phase change is known as an exothermic physical change. The heat that was added to make it evaporate, to make the liquid evaporate, is now being removed. So the heat is exiting. So think of exothermic as heat exiting. So the heat is being released or the heat is being removed and the gas is now undergoing a physical phase change to become a liquid by releasing that heat. And then another exothermic physical change is when liquid becomes a solid. So to go from liquid to solid, you've got to freeze the substance. So that also requires heat to be removed. Okay, so did you have time to think about what the intermolecular forces of attraction are holding the water molecules together? Hopefully you thought of the phrase hydrogen bonds. So take a moment to look at this graphic. Notice how fast those molecules are moving right now. It's because the temperature is high, so they're in the gaseous state. But then as you lower the temperature, notice the thermometer going down, and you get to the freezing point, look at what happens to the hydrogen bonds. Those solid lines form, keeping those water molecules sort of stuck together. Those forces of attraction develop between the slowed down molecules of water. And this is how water freezes, through the hydrogen bonds forming between the molecules of water. Once those hydrogen bonds are overcome due to the heat being added, then you have a gas. Let's now examine chemical changes. So a chemical change is when the chemical composition or the chemical makeup of a substance changes. A new substance is formed, and many chemical changes tend to be one way. And I'll explain what that means as we move through the lesson. Let's take this yellow box, for example. We've got hydrogen gas plus oxygen gas forming molecules of water. So what's happening here is a chemical change. Both of these gases are flammable gases at room temperature, but as soon as you chemically combine them and produce water, you have a non-flammable liquid. So you can see that not only does it look different, but it's a brand new substance. It's a brand new compound. And then over here in this picture on the right, you've got two separate compounds. Notice how in this reaction, the bond has broken between the green and white atom. Now notice that new bonds have formed between the green and the white atom and the other molecule. So when you notice a change in the chemical makeup, the molecular structure of a substance, then you know a chemical change has occurred. One thing all chemical changes have in common is that there is always a change in energy. So let's take a look at an example of an exothermic chemical reaction. If you've ever seen fireworks, you'll notice the beautiful, brilliant colors that are produced as a result of that chemical reaction, and you'll notice that there's a lot of light that's produced. So that release of light and heat from that explosion is considered an exothermic change because of the release of energy or the release of heat into the environment. Now, not all energy changes involve a release in noticeable amounts of heat. Sometimes just a release of light is enough to call a chemical change one that releases light or one that releases energy. So take, for example, these glow sticks. There's a chemical reaction that occurs when activating these glow sticks that releases light. Another example of a chemical reaction that releases light is one that occurs in bioluminescent animals, such as fireflies. Fireflies release light to attract or repel other animals. Now let's take a look at an endothermic chemical change. Here's an example of a cold pack. The directions on the cold pack say to squeeze it in order to activate it here. Upon squeezing the cold pack, a chemical reaction will occur and the cold pack will feel cold to the touch. So if the surroundings of a chemical reaction feel cold, that means the reaction is taking the energy it needs from the environment to occur. So when you have an endothermic chemical change occurring, the environment or the surroundings feel colder. An example of an endothermic change that involves the absorption of light energy is photosynthesis. So as you know, photosynthesis, in order for that to occur in plants, carbon dioxide, water, and light are required to produce sugar and oxygen. So sometimes it's confusing to understand the difference between an exothermic chemical change and an endothermic chemical change. So let's just take a look at these two people in the lab conducting the same experiment but with different reactants. So here on the left we have Sam, who has salt A, so basically a compound known as salt A, and he's going to add it to his flask of water. And then on the right, we have Julie, who is holding salt B, so compound B, and she will be placing that in her flask of water. They mix them both into the flask of water, and after some time, Sam here notices that his flask feels cold, while Julie says her flask feels hot. So the one that releases heat, the one that feels hot, that would be an exothermic chemical change. And the one that feels cold to the touch would be called an endothermic chemical change. Now, what it really comes down to is comparing the system versus the surroundings. So if you're looking at an exothermic chemical change, the system is the reaction that's happening in the container here. When that reaction occurs and heat is released, the environment will feel warmer. The temperature of the environment will go up, and that's how you know it's exothermic. When the system requires energy, when it needs energy, it's going to take that energy from the surrounding environment. When it takes the energy from the surrounding environment, the environment will then feel cold because it has lost that heat, it has lost that energy. So that's really the question you want to think about when you are trying to understand if the reaction or the change that you're examining is an endothermic chemical change or an exothermic chemical change. What's happening to the surroundings? What's happening to the system? Do the surroundings feel colder? Do the surroundings feel warmer? And this is not a change, this is not heat that you are adding, like the heat in a physical phase change. In order, for example, remember to boil or to melt something, you would need to add heat. Here, we're not adding any heat. We're simply mixing two substances together. We're mixing two chemicals together in a flask and observing what occurs. So there's no stove here, there's no oven, there's no hot plate, there's no Bunsen burner, there's no fire that is being used to heat up the system. The system is what's causing the change in energy, the reaction within the system. All right, let's take a look at some chemical processes and see if we understand why these are classified as chemical changes. Let's start by looking at burning or cooking. So starting with burning, this is a bonfire basically on the beach, and you can see the immense amount of light and heat coming off of this fire here. So this is an example of a chemical change because when you burn wood here, you're releasing, amongst other things, carbon dioxide, water vapor, and the wood here is turning to ash. That's an irreversible change. So that's how you can qualify burning as a chemical change. Down at the bottom, we have an egg being fried on a frying pan, and you can see that the clear part of the egg turns white in the picture. That is the denaturing of protein that is occurring due to heat being added. And that's what allows actually proteins to become more digestible when you cook the egg. So that's another example of a chemical irreversible change. Interestingly enough, hopefully you're thinking also about energy. So with the burning, the bonfire is releasing a lot more energy than the match that was probably used to start the fire. So you want to think about net energy. Where is there more energy, going in or coming out of the reaction? So in this case, because there's more energy coming out of the flame, this will be classified as an exothermic chemical change or chemical reaction. And then down here with the egg being fried, well, to cook the egg, you need to add heat to it. So that would be an endothermic reaction because you're adding heat to this process to allow it to occur. Okay, here we have rusting, corrosion, oxidation, tarnishing. So these are all chemical changes. If you take a look at the top picture of the rusty tools, these tools have been left out probably for some time, and they have reacted with the oxygen in the air. The iron in these tools reacts with the oxygen in the air to produce iron 3 oxide, also commonly known as rust. So that's a new chemical compound that's formed. And then down here we have a silver spoon. Over time, when silver is exposed to the air, it will react with the hydrogen sulfide gas present in the air and will appear tarnished, as shown in this picture. Rusting happens to be an exothermic process, one that where heat is released. Some other processes that involve chemical reactions have to be looked at a little bit more closely. The energy going in, the energy coming out is examined a little bit more closely because to the touch, necessarily energy changes aren't always detectable. Sometimes you need finer instruments, more precise instruments like a temperature probe to detect an actual temperature change that's occurring. With a fire, you don't have to do that. The change is pretty obvious. Now let's look at decomposition or spoiling or rotting or decaying, decomposing of food substances, for example. So here we have in the top picture a banana rotting. In the bottom picture, we actually have a decaying fish. So there are certain organic materials, including some plants and some organisms like fish and other sea life or insects and even rotting meat that can be bioluminescent or chemiluminescent as they decompose or decay. So that is an example of light being released or energy being released. And that would be considered an exergonic or reaction because the energy is being released. Okay, so some qualities of chemical changes that we need to make sure we understand. Whenever there's an energy change, a loss or gain of heat, not because you added heat to it or because you put it in the freezer or put it in a colder environment, no. It's when you put chemicals together and there is a change in temperature, there's a change in energy. That is an example of an energy change, and that qualifies as a chemical change. When light is produced, like with these jellyfish being bioluminescent, that's an example of an energy change because they're giving off light. Another example of a chemical change is when a new substance emerges. So for example, in this picture where you see the vinegar and the baking soda being added to it, you can see the bubbling, the foaming, the fizzing. So the bubbles that are being formed, that's evidence of a gas that's being produced. So that's a new substance. In a chemical change, a new substance is always produced, whether it be a gas or whether it be a solid precipitate. So solid precipitate is another word for residue. So in this example, you have two clear, colorless liquids in a beaker being combined, being mixed together, and then you can see them at the molecular level down below with the purple and the gray spheres. When they are chemically combined, you'll notice that there's a change evident in the form of this yellow pigment. So you can see that the atoms have recombined in the final picture here to produce a new substance. So it looks like down here at the bottom it says we have potassium iodide combining with lead nitrate, lead 2 nitrate, and then the products that result are lead 2 iodide and potassium nitrate. So the yellow solid that happens to be more dense than the liquid, and that's why it sinks to the bottom here. Looks like lead paint, yellow paint almost. So that is the more dense substance down here in the molecular view. That's the purple and gray circles at the bottom. That's settled as the precipitate. And then you have the other molecules, or the other ions rather, floating around in solution. Okay, so at the molecular level and at the macroscopic level, you can see evidence, clear evidence of change occurring at the chemical level. Now let's review by examining this flow chart some chemical and physical properties. So to understand whether you have a chemical property or physical property, you want to ask yourself this question: are these properties determined without changing the identity of the substance? If the answer to that question is yes, then we have a physical property. So if the answer is no, then we have a chemical property. The next question you want to ask yourself is, does the property depend on the amount of the substance, the amount of matter present? So if the answer is yes, then we have what we call an extensive physical property. Extensive physical properties depend on the amount of matter present. So there's usually a value associated with that property that can change, that is not constant. So for example, mass, volume, length, shape, electrical charge, all of these are examples of physical properties that have values associated with them that can change. For example, you can have 5 grams of water or 5 milliliters of water, and you can also have 5 liters of water and still call it water because it can change based on the amount present. If your answer to this question is no, the property does not depend on the amount of the substance, then you have an intensive physical property. So here is a list of some intensive physical properties: color, boiling point, melting point, density, conductivity, specific heat, malleability, ductility, luster, opacity, viscosity, attraction to magnets. Some of these also have numerical values attached to them. So like boiling point, for example, is 100 degrees Celsius for water. It doesn't matter if you have a gallon of water, a liter of water, 20 liters of water, a teaspoon of water. It doesn't matter. Whatever that volume of water is, it's always going to boil at 100 degrees Celsius. So intensive physical properties have a constant value that does not change based on the amount of the substance. Let's take another look at intensive versus extensive properties on this slide. So the top row shows you intensive properties: luster, hardness, temperature, color, boiling point. All of these are independent of the amount of matter present. Down below, when you're listing volume, when you're listing mass, when you're talking about the size, like the length, the width, the weight, the length, all of these values, all of these properties have values associated with them that can change depending on the amount of matter present. If you're looking at the luster of how shiny something is, it doesn't matter if you have 12 grams of it or a ton of it. It's going to be shiny or it's going to be dull, regardless of the amount. Okay, now let's take a look at chemical properties. So the question you want to ask yourself when you're trying to determine if the property you're examining is chemical is to ask yourself, how does the substance react in the presence of water, air, heat, acid, base, or another element or compound? Here are some additional examples of chemical properties. So when we're looking at how toxic something is, how poisonous something is, that is an example of a chemical property. When examining the oxidation state, that involves a gain or a loss of electrons during chemical bonding. So the reactivity of a substance is really what we're looking at. Heat of combustion, enthalpy of formation, they both involve the amount of heat that is released or used up in the creation of new compounds. Flammability, I think that's pretty self-explanatory, how likely it is to be engulfed in flames. Coordination number has to do with the arrangement of atoms within a compound, like what's bonded to what specific elements are involved in the bond, how many atoms a specific element is bonded to in a compound. Chemical stability and reactivity, how likely a substance is to undergo a chemical reaction. And finally, enthalpy of formation, the energy involved with forming bonds. Now let's practice what we've learned. So we're going to look at a couple slides and see what's being expressed. Are we looking at a physical or chemical change? We'll also ask ourselves, is that physical or chemical change endothermic or exothermic? Or are we looking at a physical or chemical property? And then if it's a physical property, we may ask ourselves, is this property intensive or extensive? So if we take a look at this slide, you can see that we have gallium. It's a lustrous metal with a melting point of 29.8 degrees Celsius or 85.6 degrees Fahrenheit. It can melt in the palm of your hand. So melting solid to liquid, that's an example of a physical change. That's a phase change that's occurring. So now we want to ask ourselves, is that phase change endothermic or exothermic? So gallium, the metal here, is absorbing heat from the body, causing this phase change. So because it's absorbing heat from the body to melt, we will say that that is an endothermic phase physical change. Now we can ask ourselves, is it a physical or chemical property? Well, given this information here, we've got gallium is a lustrous metal, shiny metal, and you can clearly see that it's shiny here. And the melting point is also listed. So those are both physical properties. So now that we've established that, we're going to ask ourselves another question. Is this change extensive or intensive? So think about it. Shiny. It doesn't matter how much gallium you have to observe the fact that it's shiny. It also doesn't matter how much gallium you have when you're examining its melting point. The melting point's always going to be the same for this metal. So with that in mind, we can say that melting point and the luster are both intensive physical properties because they are independent of the amount of matter that's present. Now let's take a look at this slide showing the leaves changing color in autumn. So changing color in autumn. So think to yourself, is that a physical or a chemical change? Hopefully you know that that's a chemical change based on the fact that the color is changing. Now, if we're going to look at the energy change and decide if it's endothermic or exothermic, understand that the changes that are happening within the leaf involve many chemicals. And if we're talking about the decomposition of the leaf as the seasons change from fall to winter, then I would say that we have an exothermic chemical change because the decay or the decomposition of an organic substance involves the loss of energy. Let's look at our next example. When using propane gas to grill outside, it will burn in the presence of oxygen, forming carbon dioxide gas, water vapor, and heat in the process. So do we have a physical or chemical change occurring? Well, if we're forming a few new substances, including carbon dioxide gas, water vapor, and heat, then we know that it's got to be a chemical change. Our next question we can ask ourselves, is it an endothermic or exothermic chemical change? Well, heat is being released in the process. So because of this, we know that it will be an exothermic process because heat is a product. At the molecular level, when looking at the equation, you can also notice the propane molecule in black and white here with the 5 oxygen molecules in red. These bonds between the molecules, within the molecules, will break and new bonds will be reformed, or new bonds will be formed, producing 3 molecules of carbon dioxide, 4 molecules of water, and also heat and light. So this shows you with the molecular view the changes that are occurring. Our next example shows us the density of the gray cast iron engine block in this table and compares it and shows it as being greater than the density of the aluminum alloy engine block. So let's ask ourselves, are we looking at a change? No, this is just a fact being reported on the density. So we must be looking at a property. So because it's the density that we're talking about, hopefully you realize that density is a physical property. Density happens to be the ratio of mass to volume of a substance, and it is a constant for a pure substance like aluminum. The units of density are going to be commonly grams per milliliter or grams per centimeter cubed, or in this case, kilograms per meters cubed. it's a physical property, and because I mentioned that density is a constant, that should clue you in on the fact that it is an intensive physical property because the amount of matter does not affect the property. So density, being a ratio of mass over volume, does not change. And that is unlike mass and volume individually, those properties individually, because the mass of a substance depends on the matter present, as does the volume. And because those values can change, mass and volume are considered to be extensive physical properties. And finally, our last example involves a metal being added to an acid. When that happens, as you can see in the animation, bubbles form. You can see the fizz in the picture, and the container became warm to the touch. So the environment, the container being part of the environment or the surroundings, feels warm to the touch. So ask yourself, is this a physical or chemical change? Well, sure, it looks different, but because bubbles are being formed, that's evidence of a gas being produced, a new substance is being produced, and there's an energy change due to the warm container. We can say that this is a chemical change that's occurring. Next, you want to ask yourself, is this an endothermic or exothermic change? Well, because the container feels warm to the touch, we know the surroundings feel warmer. So heat is being released. So that would be an exothermic reaction.